So now we want to introduce the idea of electric potential. And electric potential is related to potential energy in that if we take the change in potential energy of a system and divide it by the charge in that system, then we get the change in electric potential. Now we denote electric potential with the symbol V, and it turns out that really what is most important, just like with energy, it doesn't matter where we set our origin or our 0 point. What mostly matters in conservative systems is the change in our energy. The same is true for electric potential. It's really the change in the electric potential because it's the change in potential energy divided by Q or divided by the charge. It is the change in the electric potential that is the most useful of quantities. Um, and so one of the consequences that we see from this is that if I take the change in electric potential energy and divide it by charge Q, and again, for this equation to make sense, if we come back to this picture where we have the electric field between two plates, a uniform electric field between two plates, and I have my charge Q in that field, then I can calculate what the change in potential energy is. And remember that the change in potential energy is equal to negative the amount of work that the electric force does on the charge, which is negative QE delta X. And so if I take that change in potential energy, negative QE delta X, and I divide it by the charge Q, then I just get negative E times delta X. And so in a simple uniform field, the change in potential or the change in electric potential is simply the negative of the electric field times the displacement the charge Q will experience. Now, potential energy, of course, has the units of joules, but electric potential is going to have units of joules per charge, okay? Another way of saying that is going to be newtons per coulomb, right? So if I take my electric field, which is newtons per coulomb, I'm sorry, the electric potential is going to have the units of volts. I need to make that very clear, okay? So the electric potential is going to have the units of volts, and volts is a joule per coulomb, okay? Now the electric field is newtons per coulomb, and if I take the electric field, newtons per coulomb, and multiply it by the displacement, which will give me another unit of meters, then to get the voltage, the units would come out to be the electric field is 1 volt per meter. Okay, so that's what the units down there at the bottom of the screen are. But the electric potential has the units of volts, and a volt is a joule per coulomb, or energy per unit charge. So voltage, at the end of the day, is just the amount of potential energy per charge that a system has in it. Okay, so when you plug something into your outlet in the wall, for example, and it's, you know, your outlet may be 110 volts, say. So if I have a voltage of 110, then what that means is I'm going to have a change in potential energy of 110 joules for every coulomb of charge that is moved by the potential of the outlet. Okay, so that's what that means. Now, what is the electric potential of a point charge? Okay, so if you recall, the electric field of a point charge was kq over r squared, right? Kq over r squared. Now, the electric potential due to a point charge is just kq over r. So we're dropping the r squared phenomena here, okay? And that's what we have right here, right? The electric field drops off as 1 over r squared. The voltage will drop off as 1 over r. It won't be quite as steep. Now again, this is simply for a point charge. This is not for a collection of charges, but this is for a single point charge. Now, what if I do have a collection of charges? Well, that's where the superposition principle comes in. And so if I have a collection of charges and I want to evaluate the electric potential at some point in space, right? And when we do this, again, we aren't really evaluating the electric potential at a charge, right? But we're evaluating the potential at a point near a charge or near a collection of charges. And so if I have that situation, then all I need to do is evaluate the potential for each individual charge and then add it up, right? And I don't even have to worry about vector analysis here because potential energy and potential are scalars. And so I don't have to worry about the direction. I don't have to worry about sines and cosines and components and Pythagorean theorem and all of that jazz. I literally just have to calculate using kq over r for each individual charge and then add up the results because potential is a scalar, right? And that makes our calculations much easier, and that will often mean that we prefer to work with potential as opposed to the electric field because it is a scalar. Now, suppose I have two charges, right? And I have a positive charge and a negative charge, and they're relatively close together and they form a dipole, okay? So what is the potential going to look like for said dipole? In 3D space, this is what the potential is going to look like. So you can imagine if I have a positive charge sitting right here and a negative charge sitting right here, what's going to happen is that each of these charges are going to create a potential and they're going to be opposite in direction, right? And it's strictly from the fact that my Q here in the original equation doesn't have an absolute value sign attached to it. And so at some point that I'm evaluating the potential for, if I have a negative charge, then a negative sign is going to get inserted into that equation and the potential will be negative in that region. And for a positive charge, it will be positive, okay? So for a dipole where the charges are relatively near each other, then in space they're going to create these kinds of wells and spikes, okay? So hopefully that's not too esoteric or complicated, but this should also help as well. So, for example, if I just have a single charge, let's look at case A right here. If I have a single charge Q and it's some distance r from the point P that I want to evaluate the field at, okay, then what I can do is just plug those values into the equation for potential, kq1 over r, and that will give me the value. And again, if I have a collection of charges, I might have a Q here, I might have another Q here, I might have another Q here, and another Q here. And each of those Qs are going to have their own unique R, and I would just determine what each charge was. Hopefully I'd be given the charges, and I would be given the distances from the point P that I'm evaluating, and I just take all of those individual calculations and then add them up. And that would be the potential due to that collection of point charges. Now, suppose instead of evaluating the potential at point P, where it's just an empty space, right? So I'm just literally choosing some point in space to evaluate the potential. What if I place a second charge here, right? What if I place a second charge Q2? In that case, what I can do is multiply the potential kq1 over r by the second charge q2, and that will tell me what the potential energy is in the system. Okay, that'll tell me what the potential energy is in the system. Now, here's a basic problem-solving strategy for solving electric potential problems. Draw a diagram, calculate and label your distances, and then for each individual charge that you're given, you should hopefully be given the charge and the distance from the point you're evaluating at, and you plug it into the equation, V equals KQ over R, and do that for each individual charge, and you will get, add those up, and you will get the total potential. Right. Now, what about conductors? Okay, what about conductors? What if I have a conductor, say a random piece of metal, and I place some charge on that piece of metal, right? I charge it somehow, probably by conduction, right? And what's going to happen with those conductors? Now remember what a conductor is. A conductor is something that charges are free to move about on. And conductors have the property that these charges, once they're placed on the conductor, are almost immediately going to try and repel each other, and they will move to a state where they are at equilibrium. Okay, so this will happen almost immediately, right? So if I have a charged rod, I've rubbed a rod with some fur or something, and I induce some positive charge on a conductor, then those charges are going to move extremely quickly, and they're going to scatter about until they are at a in equilibrium, a system of lowest potential energy. And one of the consequences of this is that the charges will remain on the surface. Okay, all of the excess charge will remain on the surface, and they must, because if they were in the interior of the conductor, then they wouldn't be in equilibrium, and they would be forced to move until they were on the surface. So these will scatter about the surface until each charge is essentially repelled equally in all directions, and at that point you will have the conductor in equilibrium. And there are a few consequences of this. One of the most important is that the electric potential on the surface of the conductor is the same everywhere, right? So the electric potential is constant everywhere on the surface of a charged conductor, okay? Once the charges have reached equilibrium. And also the electric potential is constant inside the conductor, okay? And it is equal to the same value at the surface. Now, here is a very important consequence, okay? Here's a very important consequence of this. If we come back up here, right? If we come back up here and look at the change in potential energy, I'm sorry, change in potential, right? So my change in potential is equal to negative times the electric field times the displacement that a charge would feel in that field. If my conductor is at equilibrium and the potential is the same everywhere, then there is no change. There is no change in the potential anywhere on or in the conductor. And as a result, inside the conductor, the electric field must be zero, right? Because delta V is zero, E must be zero. And so what that means is that inside a conductor, the electric field is zero once the conductor is charged and has reached its equilibrium value. Okay, so that's a very, very important point that we need to drive home. Before we leave this video, I'm going to introduce the idea of the electron volt. Okay, so the electron volt is a unit of energy that's often used in electricity as well as particle physics. And it is the amount of energy that a single electron would gain if it were moved through 1 volt of potential. Okay, so it really is a measure of energy. So you can imagine an electron put into an electric field where the electric field is measured to be E times delta X, right? And that quantity is equal to 1 volt. And I insert the electron in that field and let it accelerate through. When it reaches the other side, if I let it start from rest and it reaches the other side, the kinetic energy that it has gained will be equal to the electron volt. Okay, so what that means is 1 electron volt is 1.6 times 10 to the negative 19 joules. Okay, so it's the same factor that we have for the magnitude of charge. Okay, so that is the electron volt. We'll see you next time.